Recording. So yeah, so like I was saying, we were talking about turning this into a mechanism for caching against the disk. Now my brain is synced up with the slides. So we talked about how you would have to extend the page table entries to support this. Remember that if we're going to support this, it was the same thing with hardware caching. If we're going to support this, we need to have a dirty bit that says whether or not the content of memory needs to be written back to the disk. And remember, the valid bit was for indicating whether or not this was present in memory. The x86 calls it a present bit, which I think is a fantastic name. And then we can use that. If the present bit is 0, then we can use the rest of the bits, the rest of the 64 bits, because remember that on 64-bit, that entry will be 8 bytes. So we can have the rest of those bytes to use to store something else, like where it is on what swap device and so forth. And this whole mechanism now requires both hardware and software support. And this is the most visible, most obvious and evident place where the operating system kernel has to mediate hardware interactions on behalf of processes. Because a process may fault, and through no fault of its own, and so then the kernel has to resolve that somehow, and it frequently may involve loading data off of a disk block somewhere and putting it in memory and then returning to that process so the faulting instruction can try again. Okay, so this is absolutely essential for building out this full virtual memory mechanism. Okay, now one thing that I'll mention, many of you have things like this sitting in front of you, or maybe in your pocket, or maybe you forgot it and it's still in your room or something like that. But cell phones, iPads, all of those kinds of devices, I mean, you might think, okay, that doesn't have a disk in it. It doesn't have, I mean, it has flash storage, but it's not going to have a spinning magnetic disk for sure. But it still has virtual memory. The reason why is because you still need process address space isolation. And in a few limited cases, you can actually evict pages from DRAM into non-volatile memory. I mean, some OSs do that. Android, I think, does that more than iOS does. But you still have that kind of a mechanism that's present there. Okay, so you'll still have page faults from time to time. But most of the time, actually, you don't have quite the same, you don't have the fullness of this mechanism where you're saving data to a swap device, because you don't really have that on the mobile device. Okay, let's see, what else? Yeah, we can implement lots of fun features. So remember that we already talked about address space isolation. That is essential. If you're going to build an OS, you have to have address space isolation. Context switch is fast. Yay, we're happy about that. We talked about all of this last time as well. But being able to memory map files into memory turns out to be super powerful, because our binary program formats tend to actually just say, here are some bytes of data, and here's the starting address that I want to have that appear in the program's address space, and here's the length of that section. And you'll have, so you have .text, .data, .ro data. That's the way those three things work. The binary file says, here's the initial contents of that memory, here's where it needs to start in the address space, and here's how long it is. And the OS carries that out. Then you have another section, BSS. Has anybody heard of BSS? You all depend on it heavily. Anytime you have a global variable that is initialized to 0, that's in your BSS section. And these are interesting because basically in the ELF file that your OS will load, I mean, this is, Windows has something similar, but it's not called an ELF file. It's called a PE file, portable executable. And it'll say, is this many bytes, but it doesn't specify what those values should be, and the OS initializes it all to 0. So that's how you have a global variable, you didn't say what it should be, it starts out at 0. You can actually kind of count on that. In fact, if you say something has an initial value of 0, the compiler will stick it in BSS because it knows it's going to start out as 0. Okay? So you have stuff like that, fun things like that going on. Okay? And permissions. Yay, we love permissions, because that means, you know, overflow exploits, buffer overflow exploits that hit the stack suddenly stop being possible, because you can say, hey, if you have any instruction fetch from the stack, don't trust it. That's a good idea for an OS to follow that. So it's you know, you see more and more of this kind of thing where you can constrain what can happen in different chunks of memory, and that makes your entire OS a little bit more reliable. Okay, so we'll talk about some of those things today. we're going to talk specifically about how Intel does this, so you can see how it's implemented. And I want to show you a few interesting things. Now, I've been telling you pretty much from the beginning of the class that the address space on an Intel x86 64-bit processor is 48 bits. That clearly is less than 64 bits. It's just because they figured 256 gigs is probably sufficient address space for, or I'm sorry, 256 gigs is even way too low for what they actually support. 256 terabytes of addressable memory is what the processor supports. At some point, they will need to grow that all the way out to the full 64-bit address space, but they're like, why right now? There's not really a huge point. There's so much I could say about that, but I won't. Pages are 4 kilobytes in size. Remember, I've been telling you that all the way along, and you've already seen that in assignment 8. Okay. Now, I mentioned that processors can also use 2 megabyte pages. I'm going to talk a little bit more about that because it's kind of an interesting characteristic of the way that addressing is done, or address translation is done. And we have a 4-level page table hierarchy. Because remember, how large would the page table be if it was a single level flat page table? 512 gigs, half a terabyte, and we have one of those for every process. Who wants to waste that much space? So instead, you have, in fact, this was a problem that I had on the last exam. I wish I could figure out where to include it. I think it would probably be a good precursor to assignment 8, because assignment 8 isn't horribly long for most people, unless you get into some debugging hell, because it is hard to debug assignment 8. But, you know, if you have a fully populated page table structure, 4-level page table, it turns out to only be 513 gigs. So even though you have this sparse data structure, it turns out that if you had to use the entire thing, it wouldn't be too expensive, too much more expensive than just the dense representation, which is kind of cool. But then the other thing is that most of the time, this data structure is very small. So with a 4-level page table hierarchy, you may have like 4 or 5 nodes for a really large program. Like, and that's what I did, is like you can use this program objdump to dump the sections of like GCC. You might think GCC is a giant program. Well, it's pretty big. But when you look at its page table structure necessary for running GCC, it's like maybe, you know, 6 or 7 of these pages just to represent the page table. So that's way cheaper than having a single flat page table for a large program. Okay. So there's some details there. We're going to talk even more about it today. All of these different levels have names, and it's really tedious. It's like you can tell they were kind of struggling for names. It was, you know, okay with IA32. They only had 2 levels, and they had the page directory and the page table. But now we have the page global directory, which is the topmost node, and then the page upper directory. So you have some number of page upper directory nodes, and then you have the page middle directory nodes, which are below those, and then the last level, each node was called a page table. Okay, and each level uses 9 bits. All the math works out perfectly, so that there's reason why they designed it that way. 4 kilobyte pages divided by 8, because we have 8-byte entries, you end up with 512 entries. Well, that's 2 to the 9. So you can use 9 bits of the address to select which one of those entries at each level. And then you get 4 levels, so that's 36 bits. And then we have 12 bits of offset. That adds up to 48 bits. Okay. So it just, they designed it so that would all work out perfectly fine. Okay. Any questions about any of this? Because this is like the foundation of what we're going to be talking about today. So does anybody have any questions? All right, so this is the idea, and obviously they're going to take this and extend it in a lot of different ways. There's something cool I'll tell you about this picture. So yeah, this is basically exactly what I was saying. You have the virtual address comes in, and it's 48 bits. I don't know if any of you noticed this, but all of your addresses that you ever seen, your debugging stuff, you're looking at this list or that address or whatever, all the way through CS24, the top 2 bytes are always 0. Okay? So that's what you notice. So it's 48-bit addresses stored in 64-bit placeholders. So you take the virtual address, virtual page offset comes straight across because it's just an offset within the block, and then the virtual address is divided into chunks, and each little chunk is used to do an index lookup at each level. So you start with the page directory base register, which is the page table structure for the current process. and it just does the address lookup all the way through. Okay? And so then the value in the page table is going to have the physical page number to go to. All right? Any questions about that? You can already see that the higher level nodes have different information in them than the bottom node, because the higher level nodes have to say this is where the next page table node is in this structure. But the lowest one, the page table thing, the thing that's actually called the page table, has a physical page number in it that's part of its entry. Okay? Now, one thing you'll notice, if you read Intel 64 manuals, which, like I said, are like 4,000 pages long, and who wants to do that to themselves, unless they're writing an OS, is that there's different page sizes. The processor, the MMU, supports different page sizes. Well, this should not really be surprising, because where the different page sizes come from is just how far you go through this lookup mechanism. So if I want to have 4 kilobyte pages, I use all 4 levels. If I want to have 2 megabyte pages, I only use 3 levels. And the third level, the page middle directory entry, will point to the start of a 2 megabyte page, okay, which is kind of weird. But if you think about it, like each one of those entries in the lowest page table node, each one of those entries corresponds to 4 kilobytes of address space, right? So if I take 4 kilobytes and I multiply that by 512 entries, I end up with 2 megabytes of address space. And so that's why if we want a 2 megabyte page, we can just do 3 levels of addressing and just throw the last level away. You can also do what is like the top 2. I think that's 512 gigs. You'd have to do the math. I'm not trustworthy when it comes to basic math. But whatever it was, like, so you what is it? Take 2 megabytes? No, maybe it's 1 gigabyte. I think you can have 1 gigabyte pages. You only have the top 2 levels of addressing, and so forth. So this mechanism can be used for pages of different sizes if the OS decides it wants to do that. Now, you might ask the question, why in the world would the OS want to have different page sizes? That seems complicated, and you could imagine if it's using pages for DMA transfers, it may want to have much larger buffers. Or the other issue is that there's some permissions that are only available at certain levels in this hierarchy. So like you may not be able to specify an execute bit at the page table level, but you can specify it at the page middle directory level. And so you would say, yeah, this 2 megabyte chunk has no execute bit, or it has an execute bit. Okay, so there's various reasons why the OS might choose different page sizes for different regions. Okay, fortunately, that's just esoteric information that you don't need unless you decide to write an OS that uses all this stuff. Okay, so processes have their own page directories. Each process has its own virtual address space. Yay, go us. And then the second point has changed a little bit in the last 12 months. The page directory also maps a very small amount of kernel code and shared library code. Shared library code is actually always going to be there because that's a good idea, but that'll also be mapped into the process's address space. So you can imagine that there may be physical page frames that make an appearance in many different programs' virtual address spaces because they're shared, and we might want them to be read-only. Okay? There was something else that I thought would be interesting to tell you all. What was it? It'll come to me. If it's that cool, I'll remember. Okay, now the page directory base register on the Intel processor is called CR3, Control Register 3. It's got like 6 control registers that you can use to control all the really basic stuff, like what operating mode is the processor going to be in, what addressing mode is it going to be in, and so forth. You can control a lot of that stuff. When you have a page fault, one of those, I think it's CR5, has the address that caused the fault, so that you can go put that somewhere, and then obviously you could pass that back to the user program like we do in Assignment 8 or stuff like that. But anyway, Control Register 3 is only controllable or modifiable by kernel mode code. And so that's smart, right? We only want the kernel to be able to change the page table structure. The user program has to ask by using mmap or sbreak or any of those kinds of operations. Okay, let's see. So basically, the way these entries work is the bottommost bit is the present, aka valid bit. So that's the bit saying whether or not this page table entry or page directory entry actually has information in it or if it should be ignored by the MMU because, well, the OS hasn't actually done anything in that address mapping. Okay? And so, if an access ended up getting to an entry where the valid bit was 0, what happens? We get a fault. And then the OS has to step in and figure out what to do. Okay? So, we have something like this. Present is 0. All the other bits are available for the kernel to use. And the way that Linux worked, I don't know how it works in 64-bit Linux, but I imagine it's probably very similar, is that it'll take those bits, and some of those bits will be devoted to identifying the swap device. And then the remaining bits will be used to index into that swap device where is this block of data actually stored. Okay, so that's one way that you can use this. Another way you can use this is have a pointer stored in there that points to more information about that address range. So that's another way that OSs will handle this. And if you think about it, that thing that describes that address range is probably always going to be quad word aligned or something like that. So the bottommost bits are always going to be 0. So that works perfectly with having the present bit being 0. Okay? Any questions? So that's the easy part. Complicated part is when present bit is 1 because you have all this junk to describe that address range to the MMU. Okay? And this is just a small amount of the information. I'm just trying to give you a sense of what it looks like. You'll notice again that the page directory address or the page table address that's stored there, now that's a physical address. Okay? So that part's complicated enough by itself. The OS, sophisticated bookkeeper, but it is just a bookkeeper. We got to keep track of the physical page and what virtual address it maps to and so forth. But you'll notice that that's in position bit 12 to 62. Okay? So that means that we could take the physical page number with zeros in the bottom part because we don't care about the physical page offset, and we can just bitwise OR in all of the other control values saying what is special about this address range. Okay, so we can go ahead and put all that stuff here. Here's the page table entry. Okay, you'll notice there's a lot of overlap. You have this A and PCD and PWT and US and RW and all that malarkey. We have all of that stuff. So we'll just describe most of these things for you quickly because they're actually pretty straightforward. You've already seen these concepts. Okay. So you have the low bits. Remember that bit 0 is the present bit. That's why we're not talking about it. But bit 1 says, is this address range read-write or read-only? So are we only allowed to read it or are we allowed to write to it as well? Okay. And then you have another bit saying whether or not it is supervisor mode only memory, so you can only access it from kernel mode execution, or if it can be accessed from user mode, or on Intel it would be ring 3. There is an execute permission. That's way up in bit 63. So you have execute disable or, I don't know, like squinty smiley face, whichever you want to look at it as. But that's the execute disable, and that basically says you are not allowed to execute anything from this address range. And if you think about it, you're going to have memory fetches going on from the CPU to memory. The MMU knows why it's happening, though, because remember you have an instruction cache and you have a data cache, and there's different address fetches going on for different operations as the CPU is executing an instruction. So it'll say, yes, I know I'm accessing this to execute an instruction, to load an instruction. And the MMU can say, nope. The execute bit says no. Or it can say, I'm doing a data read, or I'm doing a data write. And the MMU can look at it and say, oh, execute bit is 0, that's okay. Okay, so you have this control now over what is allowed and what's disallowed. Okay, so this is great. Go us! Our computers are getting better. Now, bits 3 and 4, PWT and PCD, basically allow you to control the caching policies for that address range. Again, the way to think about all these entries is they're specifying details about the address range. So WT says, am I doing write through? So the operation always goes all the way through. Or am I doing write back, where I accumulate writes into that address range and then it's written back. Now, don't ask me how that actually is manifested in real life, because obviously if the disk is involved, then the CPU can't do that on its own. There's going to be a device driver involved, so I don't know how that actually is handled or enforced on the processor. I just don't know. Unless what that means is that it's turning off all the other hardware caches between DRAM and the CPU. It could mean that. I suspect that's what it means. And then CD is, yeah, whether cache is enabled or disabled. Okay. Now, you might wonder why in the world people would do this, and the answer is that sometimes you have peripherals that are actually mapped onto the address and data bus in some way. Anybody who's done embedded system design, I'm sad I'm going to have to stop saying whoever's done 5X, because that's not a thing anymore. But if you ever did do 5X and got to say these address lines go to this thing, and then I have a chip enable bit that goes 1 when it's accessed, the appropriate address is accessed, then you can either read or write at a memory location. It looks like a memory read or write, but it turns out you're talking to a device. And when you do that, you probably don't want the caches interfering with that interaction. And so that tends to be why people would use those bits. Okay? Maybe you have, for example, the graphics hardware mapped into a specific address range, and you want to make sure that when that write or that read occurs, that you're hitting graphics memory. You're not actually hitting your own local hardware caches. That would be a good idea. Okay? So that's an example of where you might see this. All right. Any questions about this? Okay. So bit 5, the access bit. Super helpful for implementing paging policies. And it works exactly like our weird little analog that we implement in assignment 8. When an access comes through the MMU and it succeeds, there's no faults, none of that kind of stuff going on, then the MMU will go ahead and set the access bit in the page table entry to be 1. So that now somebody, presumably the OS kernel, can look and say, hey, that page was accessed. And so the kernel can use that to tell what's been accessed and what is not. Okay? Bit 6 is the dirty bit, so that is going to say whether or not a write has occurred to that address range. I.e., the data in memory may not match what it is on the swap device. Okay? So that's those two. Any questions? Now, I mentioned this in the assignment, but I think it's so cool I'm going to tell you again. A lot of processors don't actually have these bits. Like, again, waving my iPhone at all of you. It's got, an ARM processor in it. Most of the mobile devices have an ARM processor in them. ARM means Advanced RISC Machines. And those processors do have an MMU, but the MMU's page table entries do not have an accessed and a dirty bit. So how do you tell when things are dirty? How do you tell when things have been accessed? The only way you can do it is by implementing some kind of faulting mechanism where you force a fault to identify the access. You force a protection fault to identify that something has become dirty. So the Android operating system, as it's built on Linux, and its kernel actually emulates its stuff. So it's got its processor page table, which doesn't have those bits, and it's got the OS page table, which does have those bits. So it has these two page tables it's keeping in sync. All right, any questions about that? It's pretty cool. So the processor is going to generate faults if an instruction comes through that's not happy. So if the present bit is 0, then you're going to get a page fault. Okay, and so the kernel has choices, and that's one of the things we're going to talk about today. Is the kernel doesn't always say, "Ooh, page fault, kill program." That would be a bad OS. In fact, there's a lot of ways in which you can respond to a page fault, depending on the circumstance. If you have an access that violates the protections of that memory region, then you get a protection fault. And again, the answer isn't always to just kill the program, because it may be that you are doing something clever. Now, unfortunately, the most clever thing that we talk about in this class is discussed in the lecture I'm not giving. So just look at the slides, because it's kind of cool. It's called copy on write. That's how forking is fast. All right, these things are stored in DRAM. So we have a translation look-aside buffer. The x86 processor, it used to be that they would tell you a lot of details about how the hardware caches work. They kind of stopped. And I think part of it is the caches are getting so good that who cares how they work anymore? They make everything faster. I mean, it was funny because even I was looking at the website for the textbook for this class, Computer Systems, a Programmer's Perspective, and on their website, the authors are talking about how prefetching was introduced at a certain point on these processors, so the cache performance got way better. Okay, and it's changed the way those memory mountains look when you plot out the access based on stride and all of that kind of stuff. But anyway, they don't talk about this stuff because the caches are really dang good, but also they change it pretty significantly from release to release, and so why tell people information that will become out of date quickly? But anyway, they do have translation look-aside buffers. They even have multiple levels of translation look-aside buffers. They're very clever systems. Okay? And as before, the TLB entry, remember, what comes into it is the virtual page number or the virtual address, and out comes a page table entry, so that the translation look-aside buffer obviates the need for having to go and access memory. Okay. So this is a picture that kind of looks like it. So you've got the virtual address comes out as 36 bits. The virtual page offset goes straight across to the physical page offset, because why not? I mean, wires, right? That's fast. And then the virtual page number goes into the translation look-aside buffer to see if we get a hit or not. Now you can see that it's like way more complicated than we've already talked about. Okay? Let me see if I can, you can tell that's a new slide because the animation is bad. But anyway, if we get a hit, then we can just go ahead and pull out the physical page number. Obviously, it's going to check permissions and so forth, and then that'll come down if everything's allowed and we don't get a general protection fault. And then, boom, you're done. That address translation maybe took a clock, or maybe it took no clocks, because translation look-aside buffers are super fast. Okay? But if we get a miss, then we go ahead and do the thing that we talked about. We start accessing memory. Okay? And that reminds me of the thing I wanted to tell you about. I told you that for 32-bit Intel, so we talked about IA32. I've mentioned it off and on through the term. We had two levels of page table hierarchy. Then we went to 64-bit, and we ended up with 4 levels of page table hierarchy. So here's a question for you. As the address size grows, as we scale up our virtual address range, what cost also scales with it? Should be pretty obvious. Look at our page table addressing mechanism. Yeah.
The number of references that you have to link until you go to the actual...
Yeah, that's exactly right. We have a trade-off between humongous page tables and small, that are fast, or small page tables that are really expensive. And as the address size grows, the number of indirections we have to get out to our actual physical page number grows. There was a Sun processor that had a true 64-bit address space, had 7 levels of addressing in the virtual to physical addressing mechanism. Now, you can either make a really powerful, sophisticated translation look-aside buffer so that you incur that very infrequently, or you have really slow address translation. So that when you want to do that, you have a TLB miss or something like that, you end up with a memory access that is the price of 8 memory accesses. That's great, because you have the access itself plus the 7 accesses necessary to do the address translation. Okay? So as you get up in address space size, you start having to carry out different approaches. There's a really cool one called an inverted page table, where you have every physical page number, you have it in an array, and the entries are virtual page numbers. But the problem is now each physical page number can only be owned by one process, so how do you implement shared memory? Not only that, when you're doing address translation, you get a virtual address, but your array is indexed by physical address. What do? Well, hashing, unfortunately. And so you'll have these processors that actually, when they have a TLB miss, what they do is they generate a TLB miss fault. Because then the kernel needs to, this is crazy talk, right? The kernel has to step in and do the hashing, go to the inverted page table, navigate through overflow bins until they find the lookup, and then they can do the address translation. So it's interesting. This may look very sophisticated, but it has a problem that as you grow the address space, this translation mechanism will start to struggle and groan. And so we have very sophisticated translation look-aside buff. I might tell you another story today. You can tell that I'm like in total last lecture-itis mode. I may tell you a little bit about that. But yeah, sophisticated TLB lookup mechanisms. We may have a situation where we have every part of the TLB entry except for the last part. So we have the virtual address, and it has part that's the index for the page global directory, the part for the page upper directory, this part for the page middle directory, but then the page table's wrong. But at least we have all of those other things, and so we get a partial TLB hit, and we can pull out some of that information. Okay, so this is a TLB miss. So this is when we're really sad. We're going to get the cost of every access. That makes us sad. But yeah, TLB hit, blah, blah, blah. It's the partial hit. This is where TLBs are getting really clever. So that even if we don't have the full address translation cached, if we have 3/4 of it cached, we'll use 3/4 of it and then only incur the cost of the page table lookup. Everybody got that? It's quite clever, you have to admit. Are there any questions about this? I hope nobody's just completely lost, because this stuff is really cool. Again, not that you have to know it for this class, but it is really, really cool. Let's see. What was the other thing I wanted to tell you about? Oh, yeah, I wrote a program. This is my story time, Donnie's story time. I wrote a program that I was thinking about putting on the final, and then I decided not to because the results are not as unambiguous as I would have liked for a final exam problem. I don't completely hate you guys. I want to make sure that you have tractable problems. But anyway, what I did was I actually wrote a program where I was just accessing a fixed number of cache lines that would always fit in L1. But then I spread them further and further apart so that you're skipping giant chunks of memory as you go from cache line to cache line. That should not cause any cache misses in L1 because everything fits in L1. But what it should do is generate TLB misses. And you definitely notice that certain ranges of addresses, when you would access them, were way slower than the L1 hit cost. You know, they were way slower than 7 clocks or whatever the hit cost is for my laptop. They'd be like 50 clocks or 100 clocks. And I think it was because you were starting to generate TLB misses and it was incurring additional lookups because of the address translation mechanism. Okay? But then the program doesn't generate uniform results. Like if you move the mouse, you know how these stupid things are. You switch to another program or you're running some program that uses memory heavily. Well, you're already generating TLB misses from that because every time you switch page tables, your TLB is out of date. So you got to flush it anyway. So there's a lot of nuance. There's like so much sophistication that goes into this part of the system so that the virtual addressing mechanism can be fast. It's got to be fast if programs are not going to suck. All right, any questions about that? I have another story for story time, but I'll tell you maybe another time because unfortunately there's something else that's cool that I want to tell you about. Okay, so the kernel plays an important role, blah, blah, blah. Hopefully you've already seen this. Processes have their own virtual address space, and so forth. How is this stuff used for Linux? We'll talk briefly about 64-bit Linux. This tends to be the way that programs are laid out. More or less. Because remember, we have this weird address space layout randomization thing, which is a really smart idea for making sure programs aren't as easy to compromise. But you do have this cutoff. Notice 0x8 and then like all the zeros. Okay, so if you look at that, that's the 128 terabyte boundary. Below that belongs to the user program. Above that belongs to the kernel. Now that is the boundary. That's not that all of that memory is available because obviously you may not have that much physical memory even on a disk. Like I don't have a 128 terabyte drive available. It would be cool if I did, but I don't. Okay. So part of this is devoted to the kernel, and part of it is devoted to the user program. Now, here's what's changed, and this was the reason why Donnie's story time will have to be cut short. Notice that I have here that the kernel code and global data is above this 128 terabyte address boundary. There's some of it that is there for every process. It'll be unique per process. Some of it is identical because it's global information that the kernel needs to do its thing. Because remember that when we context switch, we come into the kernel on one process's address space. So you have all the stuff mapped in for the kernel. But then we dispatch, and we end up leaving on another process's address space. So if those two processes have the kernel mapped in exactly the same way, then when the kernel does the dispatching, it won't see everything change out from under it. The only part that actually changes is the user space, part of the virtual addressing. The kernel space is identical. Okay? So anyway, you have all of that kind of stuff that goes on here. And the kernel has to have some sophisticated stuff. Now, let's see, system calls. So yes, easy to make system calls. But this is where we started to run into problems about a year ago, or maybe I should say like 6 to 8 months ago, because of these exploits that are using a side channel attack to leak information from kernel space into user space. The ideal is that the MMU is supposed to prevent all of that stuff in hardware. If I have data in kernel space, then user mode code is not allowed to access it. Everybody got that? I mean, that seems like pretty straightforward, right? That's a good idea. The problem is, and I'll tell you about Meltdown, because Meltdown is sort of the real, collective brain fart, let's say, of Intel, that they even allowed this. Instructions take several cycles to execute. I mean, they have multiple phases that they go through. You have loading the instruction, you have decoding the instruction. I think you guys got to see that on the midterm, the basic idea. You have calculation, so we pull values from memory, we do calculation, and then we have to push those things back, and then we have a resolution phase at the end. So since these processors can't be clocked any faster, without burning them up pretty much at this point, we have one instruction that is in fetch, another instruction that's in decode, another one that's in load data, another one that's in calculate, and so forth. Okay? And not only that, but we have instructions that are conditional. We don't know how they should behave. So the processor guesses now. We call that speculation. It speculates that you're going to follow this branch, or you're going to do that conditional move, or you're not going to do that conditional move. Okay? Now the problem is, if you have a speculative operation that involves user mode code talking to kernel space. AMD was more clever than Intel. What they said is that if you have a speculative access from user mode code into kernel space, don't allow it. Just wait until you get to the resolution phase and see if it's even allowed, and if it's not allowed, generate a fault. Okay? The reason why you would wait till that point, you don't want to do it right away, is because you don't even know if you're going to get to that instruction. Maybe you're going to have some other instruction that branches away before you get to that bad instruction. So you don't want to fault until you get to the resolution phase. Okay? But Intel made a bad choice, and they speculatively do that access. So once you do that access, you now have some information that may be loaded into the cache that shouldn't be loaded into the cache. And that's a problem. Okay? And so you can build an exploit around this. It's a timing side channel because you can measure the timing of different accesses to memory, and you can see what information has been loaded into cache from what address. Okay? So that's part of the issue. And the way that they had to solve this for Intel, make sure we're not doing bad on time. Yeah, we're not doing bad on time. Is they make sure that the important kernel information is not mapped into the process's address space any longer. They just have a little bit of kernel code mapped into the process's address space to handle the syscall. Once you get into the kernel, now you're safe, and you can then have the kernel switch to a different page table that actually has all the kernel data loaded. What a giant pain in the behind. Okay, but this is the fix. This was what was necessary to work around this limitation that speculative memory accesses are allowed and performed against kernel space from user mode code. Giant pain in the butt. That's why people, if you heard people talking about, well, this is going to make system calls slower. Hopefully you all understand now why that is. Because now we have to change the virtual addressing information, and that means TLBs are out of date and blah, 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 right? It gets slower. Okay, any questions about that? I could give you a lot more information about how that exploit works. It's quite an interesting thing, and if I had like a bundle of energy, then that would probably be one of the fun things you get to do on the final exam, is actually figure out, how to implement a meltdown exploit. But I was too tired to do that. Okay. Because it's not exactly what I said. You have an access that goes against kernel space. What you have to do is figure out a way of doing something against kernel space that changes something in user space that you can actually detect. And so typically, every problem in computer science, including building exploits, is solved by adding another level of indirection. And so what you do is you do an access that's based on the value of something in kernel space that affects something in user space. And then you can probe the caches, and using high precision timing, you can identify what was the thing that was accessed. That allows you to infer the value of the thing that you looked at in kernel space. Now you've leaked information. There's meltdown in a nutshell. Okay. Any questions? Okay, there you go. So that's why this picture was really nice until last year, and now we're all sad because speculative execution trying to make things fast. Okay, let's see. Process-specific structures. I'm not going to spend very much time talking about this. The kernel stack is actually really important and really cool. When you guys built your user space threading library in assignments 6 and 7, that is nearly exactly how kernels work. And that is one of the first things you run into in 124 is finishing out that kernel threading mechanism in an OS. It's really cool. So that's one of the first things you do. So that's why I really love that pair of assignments, because it really exposes you to how kernels really work. Let's see, blah, blah, blah. We won't talk much about that because who cares? Now, this is probably the other important thing to talk about. We'll see if I can get through it in the last 8 minutes. This is the kind of information that Linux keeps track of. Remember that you have the page table information that the CPU needs. The MMU uses it. And then the OS also keeps track of what the virtual address space looks like. And this tends to be the way that Linux does it. You have these VM area structs that are chained together into a linked list. It's an ordered linked list where the VM start and the VM end say, this is an address range, and then the rest of the struct says, here are some details about this address range. So you can see, just like I have in the picture, that you'll have part of it that says, here's a shared library. You'll have another part of the picture that says, here's another shared library. Here's the data section of the program. Here's the text section of the program. This is the file that is being taken from. Here are the permissions for accessing it. When you guys are calling your mmap and munmap and mprotect calls, you are manipulating this data structure like crazy. So it's a good thing it works properly. Right? There was a root privilege escalation exploit a few years ago in mmap. Let's say it was like 10 years ago, I think. It was relatively shortly after I started teaching. And so you can imagine how this could be buggy, but thankfully it's not very buggy. Okay, so that's what... Oh, and you also have the PGD. What's the PGD? Page Global Directory Entry. So that's the page table for the process. But then it also has the Linux OS level description of the address range as well. Okay? So we have all of these things. I already told you about all of this stuff. Now, here's the thing. Normal memory accesses, where the MMU doesn't need any intervention, this stuff is never touched. Why would we? The processor's got its own page table. It doesn't need to look at this stuff. This is for the kernel to resolve faults. Okay? So normal page accesses, normal memory accesses, this information isn't used at all. It's only when we have faults, which are generated by accesses. Remember, the page table structure will have present bit of 0 somewhere, and so now it generates a fault, and the kernel has to step in and figure out what to do about it. That's where this data structure becomes really important. Okay? Lots of different reasons. You could have an invalid access. You try to write read-only memory. You try to access kernel-only memory, something like that, because you're trying to implement an exploit for a final exam problem that only exists in Donnie's brain. Sadly, you have a valid access. You have an access that is against an assigned address range, but the memory is paged out. So you get a fault, and you have to page in that memory. That should be allowed. Okay? Or you're accessing part of the program, and that page hasn't been loaded yet, or the heap, or whatever. Okay? So the kernel uses this data structure to answer those questions. That's basically how the kernel makes its decisions. And so a lot of times this is called a supplemental page table. Not always, but you'll definitely see that in 124 if you take that class. Because this information is at a higher level of abstraction. The OS kernel needs it to answer these kinds of questions. Okay? So let's say that the program accesses a non-existent address. I should really have it at the bottom because we all do it all the time. I dereference null for some dumb reason, and now my program's sad. Okay, so how does that manifest? You get a page fault. And the kernel looks at the VM area structs for the program, and it says, does this address fall in the range of any of these addresses? Okay. So it looks, and if it doesn't find an entry that corresponds to the address that was accessed, it says, I know this is not a mapped address. It's not a valid mapped address for this program. So it generates a SIGSEG-V, sends it to the process, and typically that'll just kill the process, unless you're doing crazy Homer Gate stuff, right? Where you say, I want SIGSEG-V to mean something. Okay, everybody got that? So do you see how this data structure is used? It's really cool, right? If we have an access, let's say it's a write, and we know it falls in a VM area struct, then we have to see if the operation is even allowed. So you can see in this case we have a write to something that should be read-only. Okay? So the MMU generates a protection fault, and again the OS looks at it and says, you know what, this is to a read-only section. So again you get the SIGSEG-V. I believe that's what you get. So anyway, again the program can be terminated. If you have a situation, okay, so let's look at where we're at right now. We got a fault. We look through the VM area structs. We know it falls within a valid address range for the process. We know the permissions are allowed. We think. Okay? There's other tricky, cool things you can do with it. See the next slides that I'm going to put up. But anyway, we know that it's okay. Then we know, oh, okay, maybe I need to load a page into memory, or maybe I need to allocate, sort of do the demand allocate thing for that memory access. Okay? So we select a victim page to evict. Again, that'll go against the physical page frames. I got to free up a frame. Okay? If it's dirty, write it back to disk. Now already this might suggest something. You know what would be really cool is if I picked a victim page that was not recently accessed and also not dirty, because then I don't have to write it back. That will have the time it takes to resolve this fault. Right? So, but you can have the OS make these various decisions. Load the requested virtual page into memory, and then return from the fault handler. Okay? So then when you return back, obviously you're going back to the instruction that caused the fault. You try it again. And hopefully if your OS doesn't suck and you don't have heavy memory pressure that made the page you just paged in get paged out again, it's the worst, then the instruction will succeed and the program will go happily on. Okay? Any questions about that? Now, there's so much nuance here, and that's why I'm super excited that anybody who takes 124 gets to build this. It's like implement virtual memory for the operating system in this directory. You go into the directory, and it's completely empty. So you get to build the whole thing from scratch and decide how to answer all these questions. Okay? There's a lot of interesting issues. And the way that Real OS has solved this, yeah, I have a little bit of time, I'll tell you. Yeah, so Donnie's story time, since I already told you this before. A lot of times what OSs are doing is they're trying to proactively make sure that pages are in a good state to resolve faults quickly. And so if you have dirty pages in memory, the OS in the background will be going through those and saying, you know what, this dirty page, write it back. Hey, here's another dirty page. Go ahead and write it back. So it'll be doing this at some slow rate as the computer is doing its thing, so that those dirty pages can now be clean. And then evicting them is much cheaper than evicting a dirty page. Okay. Now, even when you're evicting a dirty page, you may notice that, well, a lot of times we're going to hit that path where we have to load a page from swap into memory. That's slow. So page faults, we talked about this 1 or 2 lectures ago. Page faults are almost invariably this massive opportunity to do a context switch to a different process, because that process is now going to be paused for milliseconds while that page data is brought into memory. Okay, that's why we don't want to have too many faults, but we actually don't mind them too much because it certainly will end a CPU burst and allow another process to run as well. So it's not actually the worst thing in the world to have any faults. But yeah, you can tell people that. It's okay to have some faults. It's actually good. But having a ton of them starts to overflow the capabilities of the I/O subsystem, and then you have the entire system start to crawl. Okay, any questions on any of that? All right, so let me show you again, just to reiterate the plan. There's a few higher level abstractions that are really cool, but they're not necessary to talk about. And since we only have one more class, we need to use it for the final exam review. So I'll go ahead and post that material on Moodle so that you can review it. And if you love the dulcet sound of my voice, then you can watch last year's version of that lecture. And on Wednesday, we'll have the final exam review for those who are excited about such things. So anyway, we'll see you then.